every linear transformation has associated to it some very important vectors and some values that correspond to those vectors. The vectors are called eigenvectors. They're also called characteristic vectors, and sometimes eigenvalues are called characteristic values. Geometrically, they have a really, really nice description. What I would like to do is just start with one that's really easy to see. So this is just an example. I'm going to write down a linear transformation. And see what we can do with this. I'm going to say make this one say minus 0.5 and 0 and something like 0.3. Now, to be an eigenvector means that when you plug in the vector into the linear transformation, it just purely gets stretched. So for example here, I can plug in the vector 1, 0, and when I multiply this, I wind up getting the vector minus 0.50. Now you're going to notice that that's actually minus 0.5 times the original input. That's what it means to be an eigenvector. It means when you plug in the vector, the answer is a multiple of the original input. The 3 being down here is also very suggestive. This is one of the main reasons when you took linear algebra that they were so fixated on diagonal matrices. I'm sorry, when I plug in 0, 1, I get the vector 0, 3 as an answer. I can pull the 3 out in this case, and I get 0, 1. And so here you can see that the vector 0, 1 is an eigenvector, right? And its eigenvalue is 3. This doesn't mean that every vector works this way, by the way, right? If I try plugging in 1, 1, what am I going to get? I'm going to get the vector minus 0.5, 3, which is certainly not a multiple of 1, 1, right? The vector 1, 0 is a very important one here. The vector 0, 1 is a very important one here. And it actually, in terms of the graph of the linear transformation, has a very important description. Remember, when we plug in 0, 0, we get 0, 0. Now, when we plug in 1, 0, we got negative 0.5. You can see that the answer vector is a multiple of the original vector, and when the eigenvalue is negative, it turns the vector around and points it in. We saw that 0, 1 was an eigenvector, but that vector got stretched by a factor of 3, and so it goes like this. So you can see that an eigenvector with a positive eigenvalue just gets stretched and points further away along the same line. When an eigenvector is negative, it points the opposite direction along the same line. So we should very often be able just to look at graphs of linear transformations and see what these, at least the signs of the eigenvectors and eigenvalues are. Now, let's put down a different linear transformation. This is a second example. And this one has what I think are some pretty wacky numbers. I want 8, 15, and minus 2, minus 3 times xy. Now, by the way, when we plug in 1, 0 here, we get the first column here. So 1, 0 definitely wasn't an eigenvector. When I plugged in 1, 0, I did not get a multiple of 1, 0. So that's not an eigenvalue of this one. Eigenvector, sorry. When I plug in 0, 1, which is the second column of the identity matrix, I get the second column here. And so 0, 1 was definitely not an eigenvector. That doesn't mean there aren't any eigenvectors. It means we're going to have to work to find them. For example, if I take the vector t, the linear transformation t, and I try to plug in 1, 3. Well, I know what I'm supposed to do here. I'm supposed to take 8, 15, minus 2, minus 3, and I'm supposed to plug in 1, 3. And what we're going to get is 8 minus 6, that's 2, and 15 minus 9, that's 6. So when we plug in 1, 3, we get 2, 6. And by the way, here I can pull out that 2, and I see that in this particular case, 1, 3 got stretched by a factor of 2. So that's going to tell me that 1, 3 is an eigenvector, and the eigenvalue corresponding to it is 2. But you see that the 2 doesn't show up anywhere clear in the matrix. One more example. Every n by n matrix at least has n eigenvalues. Let's plug in a different vector. And I'm plugging in -2 and -3. And I know what I'm supposed to do. I'm supposed to take 8, 15, -2, -3. No. I want to plug in 2, 5. At least I think I need to plug in 2, 5. We're going to see. What am I going to get here? I'm going to get 16 minus 10, that's 6. And I get 30 minus 15, that's 15. Now in this particular case, we can see we can pull 3 out. Oh, and there's our original input matrix again. Input column, sorry. So what do we see here? We see that the column vector 2, 5 is an eigenvector here, and its eigenvalue is 3 because it gets stretched by a factor of 3. 1, 3 is an eigenvector because when we plug it in, the answer is 2 times the original input, and it gets stretched by a factor of 2. All right, I'm going to give you an activity where I'm going to give you the matrix and 2 vectors so that you can find the eigenvalues for yourself for that example.